Hi guys, welcome back. In this video we continue the discussion of determinants, and I'll remind you about some examples that were done in the previous set of videos, including these ones, where we're asked to find the determinant of a constant or a scalar multiplied by an identity matrix of a certain size. Now I'm going to solve these problems in two different ways. One way will involve drawing out what the matrix is, and another way will involve a shortcut. So first, let's draw out what this means. 2 times I5. I5 is a 5 by 5 identity matrix. So 5 rows, 5 columns, and all the entries are 0 except the main diagonal, which is all 1s. Oh. Okay, so we have 2 multiplied by that. Recall that when you multiply a scalar by a matrix, it multiplies every entry. 2 times 0 is 0, so the 0 entries stay the same, but the 1 entries become 2. 2. Okay, and then the determinant of a diagonal matrix is the product of the terms along the diagonal. So this is the diagonal matrix shortcut. So determinant of A, or determinant of 2I5, is 2 times 2 times 2 times 2 times 2 from that shortcut, which is 32. And then here's the shortcut. Actually the shortcut is one part of the lesson today. Let's see if after the next example you can infer what the shortcut is. So for the next matrix we have negative 3 times I4. So negative 3 times a 4 by 4 identity matrix. Okay, and when we multiply a matrix by a scalar, the scalar multiplies each entry. The 0 stays 0, and the main diagonal will become negative 3. Okay, now we can take the determinant. Oh, this is B, I called it A. Be consistent with the names. So the determinant of B, wow, I'm having trouble writing today. It's also a triangular matrix, or diagonal, rather, diagonal matrix. So we can use the diagonal matrix shortcut, which is the determinant will be the product of the terms along the diagonal. So we will have negative 3 times negative 3 times negative 3 times negative 3, which is 9 times 9, which is 81. So those are the answers for the first two, done using a shortcut, but not the shortest of the shortcuts. There's actually a shorter shortcut, we'll see later. Okay, here's another example. We're asked to find the determinant of 3A. So determinant of A is equal to 1 times 2 times 1, which is 2, using the triangular matrix shortcut. So for a triangular matrix, the determinant is the product of the terms along the main diagonal, just like for a diagonal matrix. So you might think determinant of 3A, is that 6? Do I just multiply the 3 and the 2 together? But let's construct the matrix and do this carefully. Determinant of 3A is the determinant of, let's replace all those entries by whatever they are times 3. So 3, 3, 3, 0, 6, 9, 0, 0, 3. Okay, and now we still use the triangular matrix shortcut, so it'll be 3 times 6 times 3, which is 18 times 3, which is 54. So it is not as simple as just multiplying that constant by whatever the determinant of the original matrix is. Might as well circle the right one, E, 54. Okay, another example, if it says find the determinant of 2a if the determinant of a is equal to 10 and a is 4 by 4. So I'm just going to make up a matrix. For the sake of argument, we could put determinant of a is 10. We could put something like this. 1, 2, 5, 1. And all of the other entries are zeros. We could make it a diagonal matrix. Determinant of a is equal to 10 and a is 4 by 4. And then multiply it by 2. So 2a is then going to be 2, 4, 10, 2, zeros everywhere else. So the determinant of 2a is equal to 2 times 4 times 10 times 2. So 2 times 4, 8, times 2, 16, times 10, 160. But this should make you uncomfortable. In order to solve the problem this way, I had to create a fake matrix. I had to say, well, this matrix has a determinant of 10, and then I'll just multiply that matrix by 2. No, but someone else might pick a different matrix. They, instead of having 1, 2, 5, 1, they might have 10, 1, 1, 1. And what's going to change? Are you going to get a different answer if it's 10, 1, 1, 1? No, you're not. You're going to get multiplied by 2, 20, 2, 2, 2. So 20 multiplied by 2, 40 times 2 again, 80 times 2 again, 160. It works out no matter what matrix you construct with a determinant of 10, or determinant of anything, but in this case 10, the determinant of 2 times that matrix is going to be 16 times the determinant of A. Where did the 16 come from? So what's happening when we multiply is that this will multiply each entry by 2, including each entry along the main diagonal. So if we were to think of this as that a diagonal matrix or a triangular matrix or any other type of matrix, I erase that point because we don't even need that. It can be any type of matrix. So we'll multiply each entry by 2. Even with a cofactor expansion, we go back and think about what that means for the cofactor expansion. If we multiply each of those entries by 2, we're going to multiply each of those submatrix determinants by 2. So what's going to end up happening is that our determinant of 2a will be, and here's a shortcut to the shortcut, okay? Shortcut to the shortcut. It's going to be 2 to the power of n times the determinant of a. For a square matrix, you can't take a determinant of a non-square matrix, so it's kind of superfluous, or it isn't necessary to say this, but I'll say it anyway. For a square matrix of order n, and that means n rows and n columns. The fact that this has 4 rows and 4 columns, so it's an order 4 matrix, means I have that 2 to the power 4 out front. So 2 to the power 4 times the determinant of A, so times 10, so 16 times 10, which is 160. So that's the shortcut to the shortcut. You can do it either by imagining a matrix that has a particular determinant, multiplying it by 2, and then finding the determinant of that, or by just saying no matter what the matrix is, I'm gonna have a 2 multiplied by each of the entries. And that's going to multiply each of my submatrix determinants by 2. And if I have to do that several times, like, well, how do I say this? Every row gets hit by 2. So every row that enters into your cofactor calculation gets multiplied by 2. So if you have 2 rows in a 2 by 2 matrix, each of those rows gets multiplied by 2. You're going to get a total multiplication by 4 for that determinant of that 2 by 2 matrix. And then you'll have another 2 coming from the Aij term in front of the cofactor. So just long story short, if you have an n by n matrix, the determinant of a constant times that matrix is going to be the constant raised to the power of n times the determinant of the original matrix. So we've seen a few shortcuts for determinants and a few not so shortcuts. We saw that for 2 by 2 matrices, it's not necessary to have a shortcut. The formula is fairly simple. It's a down product minus an up product. We saw that the formal definition of a determinant is given by this cofactor expansion. For anything larger than a 3 by 3, this is the only method we have right now. For a 3 by 3, we have something called the secret method, which is in the videos and in the notes. We have, beyond that, we have shortcuts for only special types of matrices. So if A is triangular or diagonal, we have a nice shortcut for calculating the determinant. Or if A has a row of zeros, a duplicate row, duplicate column of zeros, or if any 2 rows or any 2 columns are scalar multiples of each other, then that tells us that the determinant is 0. The one above tells us that the determinant of A equals product of diagonal terms. So product just means multiplication, and the other ones are formulas that are formal. This is not close to being good enough of an arsenal for calculating determinants, especially for large matrices. So let's say we have a big matrix, 7 by 7, 6 by 6, something like that, and we want to find the determinant of it. You don't want to be stuck doing cofactor expansion. So then you look for other shortcuts. You look for 0 rows, you look for diagonal, triangular, 0 columns, you look for duplicate rows, duplicate columns, or scalar multiple rows, scalar multiple columns. And ideally, we would never have to do cofactor expansion ever again, except in places where the question has been cooked. That's the only approach that will work, and we'll see one of those in the lesson today. But for the most part, except for a few fairly artificially constructed questions, it will be possible after today's lesson to completely eliminate cofactor expansions. What we'll do is we'll turn your old enemy, the thing that you used to hate the most, which was row reducing a matrix, we'll turn that into the enemy of your enemy, which sometimes means that this is now your friend. What we'll do is we'll do some experiments, some mathematical experiments. We'll see what will happen to the determinant of a matrix if let's say I multiply a row by 2. What happens to the determinant? Or what if I divide by 2? What change is made to the determinant? Or what happens if I swap 2 rows? Or what if I replace one row by itself plus or minus multiple of another row? What impact do those operations have on the value of the determinant? If we can figure that out, if we can figure out the accounting rules for row operations as far as they impact the value of the determinant, then what that will allow us to do is to manipulate the matrix so that we can bring it into a form where the determinant is simple to calculate, like triangular or diagonal, and then calculate the determinant from there. So it opens up a whole bunch of new strategies for calculating determinants. Now, that hinges on the hope that when we perform row operations on a matrix, it makes changes to the determinant that are reliable, that are consistent. That, like, multiplying by 3 is going to change the determinant this way, and multiplying by 5 will change it some other bizarre way that isn't just the difference between 5 and 3. We have to make sure that that's not the case. Okay, so what we're going to learn through experimentation is how does a modification of the matrix get translated into a modification of the determinant, and how do we generate accounting rules for determinants, with the goal of turning a horrible matrix into a nice matrix, like triangular or diagonal. So it's really easy to calculate the determinant from there. So for this first experiment, what is this? Okay, I'm not going to follow whatever's there. For this first experiment, I'm going to take this matrix, A, and I'm going to find the determinant of A. Determinant of A is equal to down products minus up products, 6 times 3 minus 5 times 2. So 18 minus 10, which is 8. Now I'm going to check what happens if I replace row 2 by row 2 times, so let's make up a number just as part of our experiment, not too big. Let's go with 4. Let's see what happens if I multiply row 2 by 4. So then what am I going to get? 4a. It's not 4a, it's just a new matrix. Row 1 is the same, 6, 2, and then row 2 becomes 20, 12. Now what's the determinant of this? Determinant of B is equal to 6 times 12 minus 20 times 2. So 70, let's see, 6 times 12 is 60, 72, minus 40 equals 32. Now what's the relationship between the original determinant and this? So we notice 8 times 4 is equal to 32. So I'm going to summarize the results of this first experiment. Multiplying a row by a constant or a scalar results in multiplying the determinant by that scalar. Let's check columns next. Let's see if a column experiment is the same. So we have A is equal to 6, 2, 5, 3, and we'll do an experiment. So this is a different experiment. I'm going to replace column 1 by column 1 multiplied by 3. So you haven't seen that type of notation before. You're used to seeing the row notation. This is a column operation. So column 1, we have 18, and then 5 times 3, 15, and then 2, 3. What's going to happen? When we find the determinant of this, I'll call it C. So the determinant of C is 18 times 3 minus 15 times 2. So that's going to be 54 minus 30, which is 24. Our original determinant of A, 6 times 3 minus 5 times 2, 18 minus 10, which is 8. And notice the relationship between these. Notice that 8 times 3 is equal to 24. So the result of this experiment multiply a column by a scalar means we multiply the determinant by that scalar. And we'll continue with an example of a 3 by 3 in the next video.